Okay, here we go. Chemistry 3111. This is chapter 20, carboxylic acids and derivatives of carboxylic acids. Derivatives of carboxylic acids are things like acid chlorides, um, esters, amides, acid anhydrides. So we're going to see many functional groups throughout chapter 20. It says here that carboxylic acids are very abundant in nature. You know, it's not uncommon to find carboxylic acids in natural products as well as synthetic pharmaceuticals as well. You see, for example, acetic acid. I know you've all heard of that because you've all passed general chemistry too. And acetic acid is a weak acid, but it's responsible for the pungent smell of vinegar. What else? Butanoic acid. If you've ever smelled, it says here the rancid odor of sour butter, and I don't mean to be harsh or anything, but it's actually the smell of vomit. If you've ever smelled vomit, and I'm going to assume that you all have at some point, but sour butter, that's butanoic acid. Dirty socks, hexanoic acid. You're like, well, this chapter is really a good one. Lactic acid. If you've ever tasted sour milk before, it's because of the buildup of lactic acid in your milk, where it starts to decompose or rot. Another example would be aspirin, which is acetylsalicylic acid. Um, so acetylsalicylic acid, you can see the carboxyl group over here. Also, 4-amino acetylsalicylic acid. So this is used in the treatment of TB. And anyhow, you have this other compound here, which is an acne treatment that also has a carboxyl group. So it's not uncommon to find carboxyl groups all around us. And in fact, in the United States, we make about 2.5 million tons of acetic acid per year. It's the simplest, not the simplest possible carboxylic acid, but it's one of the simplest possible carboxylic acids. And what's it mostly used for? So they take methanol and carbon monoxide, they put it together with a rhodium catalyst, and it's mostly used to make vinyl acetate, which is found in paints and adhesives. So if you've ever bought paint before, it's going to have some vinyl acetate in it. There you go. So carboxylic acids are very important in organic chemistry, and they show up a lot in biochemistry too, things like pyruvic acid or malonic acid, and we'll talk about those. Okay, so monocarboxylic acids, meaning a carboxylic acid with only one carboxyl group in it, which is most of what we're going to look at in this chapter, is named with the suffix oic acid. So if you have one carbon in your carboxylic acid like this, that would be one carbon. A one carbon alkane would be methane. So this would be methanoic acid, because we change the suffix of the E and we replace it with oic acid. So we have methanoic acid, ethanoic acid, propanoic acid, butanoic acid, pentanoic acid, hexanoic, octanoic, nonanoic, and decanoic acid, so on and so forth. Now you notice that there's a hydroxyl in this compound here, but you notice that the suffix of the compound is oic acid. That means it's regarded as a carboxylic acid, and that is based on the hierarchy of functional groups. And we don't talk about that a lot in Chemistry 3101 or 3111. However, I did take it from another book and I posted it in here. So you can see that if you have a carboxylic acid, let's say, and an alcohol in the same compound, the one that has the highest priority, which in this case would be the carboxylic acid, that is what the compound is considered. It is considered a carboxylic acid. So there you go. Also, the carbon of the carboxylic acid moiety, or the carbonyl carbon, meaning this one here that I'm highlighting in blue, or this one here, that is assigned the locant position number 1, right? And you can clearly see that that is why if this is 1, 2, 3, 4 dimethyl, and then we have the 5 hydroxy out here. So the carboxyl carbon is always going to be carbon number 1 in our carboxylic acid. Now, what if you have a carboxylic acid group attached to a ring? We name that like an alkane carboxylic acid. What does that mean? It means you literally name the alkane first, and then you throw the suffix carboxylic acid on the end. So if you had a cyclohexane like this here, that's cyclohexane, and then we have a carboxyl group directly attached to it, so it's cyclohexane carboxylic acid, right? If you had this, for example, right? The condensed form of a carboxyl group is this, CO2H, and this is a cyclobutane. So this would be cyclobutane carboxylic acid, carboxylic acid. You need a lot of space to write these things down. I'm kind of getting messy here. There we go. Anyhow, there are also many common names that are used for carboxylic acid. If you only have one carbon, instead of methanoic acid, we call it formic acid. Again, this is a common name. If you have two carbons, instead of ethanoic acid, we call it acetic acid. If you have three carbons, instead of propanoic acid, we call it propionic acid. If you have four carbons, instead of butanoic acid, we call that butyric acid. There's another one, if you have five carbons, so one, two, three, four, five, we call this, instead of where's my pen? Where's my pen? For pentanoic acid. The common name for this is valeric acid. Valeric acid. Anyhow, the reason we learn the common names, you might find them a bit annoying. All of these common names, again, which are formic, acetic, propionic, butyric, and valeric. The reason that we use them is because they are common. Okay, they're very commonly used. They're used all the time by organic chemists, physicians, pharmacists. So they're very important that you know. Even biologists use these from time to time. Another one would be benzoic acid, is a common name. Instead of calling this benzene carboxylic acid, we call it benzoic acid. There's also some important dicarboxylic acids that you need to know, but I'll get to that in a second. Here's just a table. I literally took this off of, I think, a Google search or something. And this just has the first 5 carboxylic acids in a table for you. So you have one carbon, you have the common name and the systematic name. Okay, you have 2 carbons, 3 carbons, 4 carbons, and 5 carbons. And again, you might find learning these a little annoying, but I promise you that they get used all the time in chemistry, so it's very useful to learn those. All right. I mean, if you just go back here and you think about general chemistry 2, which you all passed, how many times did you hear about acetic acid in that class? All the time, but you never heard anybody ever mention ethanoic acid. So common names are common for a reason. All right, what about dicarboxylic acids? If we have 2 carboxyl groups in the same carboxylic acid, say for example here, we have a total of 1, 2, 3, 4, 5 carbons in our main chain, and we have carboxyls on each end. We would call that a dioic acid. So you'd call this pentane dioic acid. You see that suffix there. But more important, I think, than even learning how to name dicarboxylic acids as dioic acids, which again, there's some questions in the textbook about that, are learning the common names of dicarboxylic acids. So instead of calling this ethane dicarboxylic acid or calling this propane dicarboxylic acid, we much more frequently use the common names: oxalic acid, malonic acid, succinic acid, glutaric acid. So that's where we have 2 carbons, 3 carbons, 4 carbons, 5 carbons. And I'm going to add one more to it here because I know a lot of you are taking biology degrees. So if you have 6 carbons, let me just show you. So 1, 2, 3, 4, 5, 6. This one would be hexane dioic acid, right? But we call it adipic acid. So adipic acid. You probably noticed that pentane dioic acid and glutaric acid are the same, aren't they? Right? It's just we use glutaric much more commonly. Okay. And again, it's really handy to learn all these common names for dicarboxylic acids because they do come up frequently in a biology class. All right. Anyhow, my students came up with a mnemonic, I guess, a number of years ago. So if you have 2, 3, 4, 5, 6 carbons, I said it goes oxalic, malonic, succinic, glutaric, adipic. And what they came up for OMSGA was, oh my stars, not starts, oh my stars, come on Dion, there we go away. Okay, again, that's something that my students came up with. I didn't come up with that. All my stars go away. I'm not telling you to go away or anything like that. But that's what they came up with for OMSGA. Oxalic, malonic, succinic, glutaric and adipic acid. So I thought you might find that amusing. Anyhow, with all that in mind, let's take a look at this here. It says provide both an IUPAC name and a common name for each of the following compounds. We have the first one. You can see that it's got two carboxyl groups, right? So this is a dicarboxylic acid, and we have 3 carbons in the middle. So that would look like this. We've got 1, 2, 3, 4. There we go. So the common name for this is glutaric acid, right? We had oh my stars go away. So that was 2, 3, 4, 5, 6. And we have 1, 2, 3, 4, 5 carbons. So this would be glutaric acid, would be the common name, glutaric acid. Again, that is the common name. And then for the IUPAC name, we'll use red. And that would be 1,5-pentane dioic acid. So 1,5-pentane dioic acid, like that. That's something I should point out on the last slide. They left that out here. This should say 1,5-pentane dioic acid. Anyhow, let's get back into it here. The next one, we have how many carbons? We have 1, 2, 3, 4 carbons. So let's write the compound out first. We've got 1, 2, 3, 4 carbons. So the common name, let's do the IUPAC name first. It would be butanoic acid, but the common name is butyric acid. This is the one that's responsible for the smell of rancid butter. And then the last one, we just have an aromatic ring. Okay, remember that in organic chemistry, C6H5 means that you've got an aromatic ring that is monosubstituted. So we've got this like that. The IUPAC name for this would be benzene carboxylic acid. So carboxylic acid. And the common name is benzoic acid. We saw that a couple slides ago, benzoic acid. And there you have it. It says to draw the structure of each of the following compounds. So cyclobutane carboxylic acid, I think I drew that already today. So you draw a cyclobutane like that, the best square I can. And then we draw our carboxyl group attached to it. The next one is 3,3-dichlorobutyric acid. So if we draw butyric acid, we've got a total of 1, 2, 3, 4 carbons like that. If we number them, we've got 1, 2, 3, 4. On the 4th carbon, we've got 2 chlorines. So a chlorine here and a chlorine there. And in the next one, we've got glutaric acid. How many carbons are there in glutaric acid? Let's see, we've got oh my stars go away. So that's 2, 3, 4, 5, 6. So we've got a total of 5 carbons. So we've got 1, 2, 3, 4, 5 carbons. And on the 3rd carbon, we've got 2 methyl groups, just like that. So there's 3,3-dimethyl glutaric acid. Let's keep this nomenclature thing going. It says provide an IUPAC name for each of the following. So we're not giving common names, just IUPAC names. If we look at the first one, the longest carbon chain contains the carboxyl has 1, 2, 3, 4, 5, 6. We've got 4 methyl groups, 1, 2, 3, 4. So we've got 3, 3, 4, 4 tetramethyl hexanoic acid. There we go. Look at the longest chain in this one. We have a total of 1, 2, 3, 4, 5 carbons. It wouldn't matter if you went to this side. Either way, you end up with the same answer. So we've got a propyl group right here. This is a propyl group. So this would be 2 propyl pentanoic acid. And then the last one, we've got a chiral center in this one. So we have to designate this as RRS. So if we just look at the chirality, we have the hydrogen going in back. That's going to be lowest priority. This would be first. This would be second. This would be third. So we're going in this direction. So this is counterclockwise. That means This is an S compound, so we can erase all this. We have S. Then we count the carbons. 1, 2, 3, 4. We've got a 4-phenyl. Sorry, did I put a 4 there when I didn't mean to? Yeah, so we've got a, I'm like, that's not right. We've got a 3-phenyl. I'm just writing it down here. We've got a 2-amino, right? An amino is when you have an NH2. That's called an amino group. So we've got 2-amino and then 3-phenyl propanoic acid. So let's write that down. So S2-amino, 3-phenyl propanoic acid. And this is an amino acid, and we're going to do a whole chapter on amino acids later on. So later on, we'll do an entire chapter on this. But anyhow, you see you have an amine, and you have a carboxylic acid in the same compound. So that's an amino acid. The name of this compound, the amino acid is called L-phenylalanine. I do not expect you to know that for this chapter at all, but that's what you would call that if you were talking about it strictly as an amino acid, which is how most chemists and biochemists would refer to it. Anyhow, all right, let's get back into it here and talk a little bit about the structures or the structure and properties of carboxylic acid. Right, you should know that the carbon of the carbonyl group is sp2 hybridized. Therefore, it is trigonal planar, right? Trigonal planar. It's flat as a pancake. The bond angles here are approximately 120 degrees. And you should know that a carboxylic acid can form this kind of dimer that I have shown here, where it maximizes its hydrogen bonding, right? You see how there's 2 hydrogen bonds here, and that contributes to the extremely high boiling points of carboxylic acids. In fact, carboxylic acids have higher boiling points than analogous alcohols. Like, let's say, for example, if you compare the boiling points of ethanol, so ethanol has a boiling point of 78 degrees Celsius, whereas the boiling point of acetic acid, which only differs by the double bond to oxygen, has a boiling point of 118 degrees Celsius. And again, it's because of that maximized hydrogen bonding, right, between the delta negative of the carbonyls and the delta pluses on the hydrogens, like that. So again, carboxylic acids maximize their capability of hydrogen bonding. Well, I mean, if you think about the word carboxylic acid, what does that mean? What's an acid in chemistry? It's a proton donor. So carboxylic acids are not strong acids like sulfuric acid or hydrochloric acid. However, they can donate protons. So if you take a carboxylic acid, although it is a weak acid, if you put it in a strong base, so again, this is a weak acid, but if you put it in the presence of a strong base like sodium hydroxide, well, what's the base going to do? It's going to rip all the protons off of that in order to make a carboxylate salt. Okay, sometimes if we just have the carboxylate by itself, we call it just a carboxylate, but since they're showing the cation, we call it a carboxylate salt. And of course, you produce water as well. So how do we name these carboxylate salts? Well, the way that you name it is that you replace the suffix is going to be O8. So if you have benzoic acid and you make it a carboxylate, it's going to be benzoate. So here we have the sodium cation. You list the cation first, and then you put benzoate, right? Let's say you had, I don't know, let's say you had propanoic acid, right? So this is propanoic acid. Well, if you were to remove the hydrogen, you would call this propanoate. So propanoate. Then let's say you put a potassium by it. Then it would be potassium propanoate. Okay, that's the whole idea. So we would call this, oops, where's my black pen? There we go. Potassium propanoate. And something you'll notice about this chapter is that it's got more nomenclature than any other chapter in the entire book. So it requires quite a bit of practice on your nomenclature in this chapter. I just want to take a look at this whole reaction here on the top of the slide with respect to pKa's, because we know that the pKa of a carboxylic acid is, let's say it's usually around 5. Okay, let's say acetic acid is like 4.75 or something. but close enough to 5. Well, what's the pK of water? The pK of water is 15.7. Remember that the equilibrium is going to lie to the side of the weaker acid, so it's going to lie hard to this side, and that's why, again, you can use sodium hydroxide to effectively deprotonate all of the protons from a carboxylic acid. They're acidic protons. Well, here I just show the pKa's of some common carboxylic acids. Here we have benzoic acid, acetic acid, and propionic acid or propanoic acid. They have, again, pKa's around 4 to 5. So if you take a carboxylic acid and you put it in water, remember the pKa of a carboxylic acid is around 5-ish, let's say, and the pKa of hydronium is negative 1.7. Well, the equilibrium is going to lie hard to the side of the weaker acid. So this is our weaker acid. And so when you put a carboxylic acid in water, it only dissociates slightly. It doesn't ionize completely like sulfuric acid or hydrochloric acid, which are strong, powerful electrolytes. It's only going to dissociate partially, just a little bit. Now, why is that? Well, if you compare hydrochloric acid or sulfuric acid or hydrobromic acid, let's say, to a carboxylic acid, you would consider a carboxylic acid a very weak acid. But again, acidity is relative, right? What if you compare a carboxylic acid like acetic acid to an alcohol like ethanol? Well, in that case, you can see the difference in the relative acidity is 10 to the power of 11. So I'm not quite sure what that would be. That would be what, 10, that would be like 100 billion, I guess, or 10 billion. Anyhow, the idea is that a carboxylic acid is much more acidic than an alcohol. So again, it's all relative. Now, if we go back to organic chemistry 1, you would have learned the concept of aereo. If you compare the conjugate base of a carboxylic acid with the conjugate base of an alcohol, right, the negative charge is on the same atom, so you can't use atom to solve, okay? But when you look at resonance, you see how this has no resonance structures. However, this has 2 resonance structures which contribute to the overall resonance hybrid, and that is why a carboxylic acid is more acidic than an alcohol. We just used our aereo again. Extrapolating on the whole concept of aereo, you can imagine, and I'm sure you would have guessed this if I hadn't even taught it to you, that if you place electron withdrawing substituents on a carboxylic acid, they can have an effect that increases the relative acidity of that carboxylic acid. Let's say, for example, we have acetic acid, which has a pK of around, what did I say, 4.75, so round up to 4.8. Well, if you take a look here, we have 3 hydrogens on that carbon, but if we start adding chlorines, 1 or 2 or 3, look what happens. You can see that the pKa drops dramatically as we add more chlorines. Why? This is not an effect of the atom. It's not a resonance effect because all of these have the same 2 resonance contributors. It's an effect of what? Induction, right? Because we know that there's an inductive effect of these chlorines, which are electron withdrawing, and they seek or they stabilize the conjugate base that is formed after any one of these acids donate a proton. Now, that substitution of what's called the alpha position, right? If you look at your carbonyl group, we don't assign that a Greek letter, but we call this the alpha position. So as the substitution at the alpha position increases with these electron withdrawing chlorines, pKa drops. But if you put substituents like a chlorine at the beta position, it will decrease the pKa slightly. However, if you put one at the gamma position, it has basically no effect. You see the same thing, the same kind of effect of an electron withdrawing substituent on a benzoic acid derivative as well. Take a look at all these para-substituted benzoic acid derivatives, right? We have benzoic acid here, and then where Z is, it's in the para position, right? This is para. And what you see is that the more electron withdrawing the substituent is, the lower the pKa is, right? A nitro group is very electron withdrawing, whereas a hydroxyl is very slightly electron withdrawing. It's electron withdrawing by induction, but it's also electron donating through resonance. So weakly, we'll put weakly electron withdrawing, okay? Anyhow, so that's representing the effect of with electron withdrawing substituent on a benzoic acid derivative. And I'm not going to draw all the resonance contributors, but if you were to draw the conjugate base of para-nitrobenzoate, so if I draw the conjugate base like this, and I put the nitro group over here, you should be able to draw the resonance contributors that explain why the nitro group serves to help stabilize this negative charge. That, again, is something that we kind of covered in chapter 18. Well, with all that in mind, let's take a look at some carboxylic acids here. This is actually divided up into two separate problems here. And we're going to rank these compounds in order of increasing acidity. So we've got 2,4-dichlorobutyric acid. So we'll start by drawing that. We've got butyric acid, 1, 2, 3, 4. So we've got 2,4-dichlorobutyric acid. Then we've got 2,3-dichlorobutyric acid. So that means we've got one at carbon 2, and we've got one at carbon 3. And then we've got 3,4-dimethyl. Yes, 3,4-dimethyl butyric acid. So 1, 2, 3, 4. So that means we've got a methyl group at carbons 3 and carbon 4, like that. That's not even a, does that say dimethyl? I think it's supposed to say dichloro. Yeah, I think that might be a typo. I'm going to cross this out and write dichloro. That would make way more sense because this makes no sense. So let me fix this. Where's my eraser? Here we go, and here we go. So we'll put a chlorine. Here is where it was, and here. So if I call these A, B, and C, can anybody tell me which one of these would be the most acidic? Could anybody tell me which one would it be? A, B, or C do you think would be the most acidic? So in essence, what I'm asking is which one of these would, yes. Sorry, I didn't see what you had written. Skylar and Courtney are both 100% correct. So this would be most acidic, right? And again, we didn't use atom to solve it. We didn't use resonance to solve it. What was used was induction, right? Because the chlorines on this one are closer, right? This one and this one both have a chlorine in the second position, but this one's in the fourth position and this one's in the third. So B is the winner and C is going to be the loser, right? It's going to be the least acidic. There we go. I'm just going to throw this out there to my students. Let's see here. If I number these, if I call them 1, 2, 3, that doesn't really work because I want to rank them. So I'll have to call them A, B, C. So if I call this A, B, C, D, E, could anybody tell me which one of these would be the most acidic? Yeah, it's B again, absolutely. So B would be the most acidic, right? So because this is a strongly electron withdrawing group. If you take a look at the other ones, you have bromine, which is slightly electron withdrawing, but you have an electron withdrawing group here with the carbonyl. So that means E would come next, okay? Then if you look at the bromine, that is slightly electron withdrawing. So we'll put the bromine next. And then this one is going to be the most electron donating. And then this is going to be slightly electron donating. So we have D and then we have C like that. All right. And this is why you have to know your chapter 18 chemistry really well to understand what's electron donating and what's electron withdrawing. The good news is that already in chemistry 3101, so in organic chemistry 1 and in organic chemistry 2, you've already looked at some cool reactions to help you make carboxylic acids. Say, for example, when we talked about the oxidative cleavage or the ozonolysis of an alkyne, right? We covered this reaction in organic chemistry 1, okay, where you take an alkyne, you treat it with ozone followed by water, and what does it do? It breaks this bond, and you end up with 2 carboxyl groups. Again, that's organic chemistry 1. And then in organic chemistry 2, we learned benzylic oxidation. So if this is a benzyl group, or sorry, benzylic oxidation. And we also learned the oxidation of a primary alcohol. Sorry, I'm getting ahead to here. But anyhow, if we oxidize a primary alcohol with a very strong oxidizing agent, it says here an acid, remember you take sodium dichromate, sulfuric acid, and water, or you can do it in base. If you do the first step as being potassium permanganate and water, and you heat that, and then in the second step, you treat it with acid, okay? That will work too. And then where I was getting ahead on myself was this one here. If you have a benzylic proton, you can do the same thing. You can use acid conditions, or you could use these basic conditions to affect an oxidation at the benzylic position like that. So these are the ways that we've learned to make carboxylic acids already in this class. And as you can imagine, we're going to learn some other ways. There is one more way that we learned to make a carboxylic acid. If you think about it really carefully, you remember when we talked about halohydrins? This would be in the last chapter. We talked about, if I just write down a halohydrin, and I'm just trying to refresh your memory here, it had a hydroxyl group and a nitrile on the same carbon. If we treated that with aqueous acid and we heat it up, okay, we actually end up with this, where we had a hydroxyl and then we had a carboxyl group over here. Well, if you take any nitrile, okay, and you treat it with aqueous acid and you heat it up, you can make a carboxyl group. So there's a new way to make a carboxylic acid. Now, you already know how to make a nitrile because we talked about it quite a bit in Organic Chemistry 1, right? If you use cyanide as a nucleophile, so cyanide is a weak base, but it is a strong nucleophile. So if I put it in the presence of a primary alkyl halide, what's it going to do? It's going to do an SN2 reaction. You can practice your curved arrows here. Nucleophilic attack, loss of leaving group, and now I have a nitrile group. If I treat that with aqueous acid and heat, I make a carboxyl group like that. So there's a new way to make a carboxylic acid from a nitrile. Kind of cool. Well, there's an even cooler way, I think, to make a carboxylic acid, and that's to use Grignard chemistry, right? You remember how when we looked at a Grignard reagent, let's say we had some kind of alkyl magnesium bromide, for example. I said that you could treat that as if it's a carbanion, and then you have the magnesium and bromine with a positive charge. So what does that mean? It means that this is a very powerful nucleophile, right? So this is a good nucleophile. Well, where do I get carbon dioxide, right? This is actually carbon dioxide right here, the same kind of carbon dioxide that you're exhaling right now. Okay, this is carbon dioxide, but it's not in the gaseous phase, is it? It's in the solid phase. So this is dry ice. Dry ice. I don't know if I took this picture, if I took it off the internet or what. It's been there for a while. But what's cool is you can actually take a Grignard and you can subject it to dry ice. And what it does is it does a nucleophilic attack on the dry ice. Why? Because if you look at the structure of CO2, it's linear in terms of its molecular geometry, but you've got two really polar bonds here, pulling electron density away from that carbon, so the carbon is very delta plus. What does that mean? That means it's very susceptible to nucleophilic attack. If you've got a strong nucleophile like a Grignard kicking around, it's just ready to go. Wow, right? And then what do you end up with? You end up with a carboxylate. Okay? But you're not going to isolate the carboxylate. This is actually a two-step process to make a carboxylic acid. In step 1, you add CO2, but in step 2, you have to treat it with aqueous acid in order to protonate the carboxylate and make a carboxylic acid. So what does the reaction look like overall, this Grignard strategy to make a carboxylic acid? Let's say you had bromobenzene. That's the name of this compound here, bromobenzene. Well, in the first step, you would treat it with magnesium and diethyl ether to make your Grignard. So now you've got phenyl, magnesium, bromide, which is a really good nucleophile. In the first step, you treat it with carbon dioxide. And then in the second step, you treat it with aqueous acid to do the protonation. And this is a mechanism I expect you to be able to draw, right? You should be able to say, Okay, well, let me just draw the mechanism for this part here. I have my phenyl, which I can regard as a carbanion. I have carbon dioxide, like this. I have my nucleophilic attack. Oops. My nucleophilic attack will look like this. I end up making a carboxyl group, or sorry, a carboxylate, like this. And then what's going to happen in the next step is that you have your H3O plus, and your carboxylate group is going to pick up a proton from that, and then you're going to end up with, oops, you're going to end up with your carboxylic acid. And that's it, my friends. Very cool mechanism and very cool reaction, right? Because you think about it, I mean, carbon dioxide is very cheap. I mean, all you have to do is get some dry ice and throw it in the reaction mixture. Very easy to work with. So let's talk about some reagents that we might use to perform the following reactions. And I can think of a few to do the first one. If we want to take ethanol, so this is ethyl alcohol, and we want to convert it to acetic acid. What are we doing? We're taking a primary alcohol and we're oxidizing it to a carboxylic acid. We could either use our strategy in acid, sodium dichromate, sulfuric acid, water, okay? Or we could use our strategy in base, KMNO4, water, we heat that up. Then in the second step, we use aqueous acid. That would work. The next one, we want to take toluene, which is methylbenzene, and we want to convert that to benzoic acid. So what are we doing? We're oxidizing at the benzylic position, right? There's 3 protons here. I'll just draw one of them in. We're going to do an oxidation there. So again, same thing. I'll just write down sodium dichromate, sulfuric acid, and water. So that's called the Jones reagent. The next one, if we want to convert benzene to benzoic acid, well, this is a good one. If I want to convert benzene, which is this compound, to benzoic acid, right, I can think about this in terms of retrosynthesis because I'm adding a carbon. But I know that if I had bromobenzene, I could do the Grignard reaction, right? I could treat it with magnesium and ether, followed by CO2, followed by aqueous acid. So how do I get from here to here? Hey, we learned that in chapter 18. Let's write down what we know. If we take benzene and we treat it with bromine and iron 3 bromide, we would make bromobenzene like this. In the next step, we'll treat it with magnesium and diethyl ether. That's ET2O, that's diethyl ether. There we go. And now we've made our phenyl magnesium bromide. And then we're going to treat it with carbon dioxide, followed by aqueous acid. And there you go. All right. Last one is 1-bromobutane dipentanoic acid. I'm going to let you solve that one on your own time. The solution to that is in our solutions manual, which again, everybody has access to, but you can tell that you're going from butane to pent. So you must have to add a carbon in your overall reaction synthesis, just like we did here, where we incorporated this carbon into the molecule right here. Well, let's take a look at some reactions of carboxylic acids. Remember how we used lithium aluminum hydride in the aldehydes and ketones chapter? That would be chapter 19. We used lithium aluminum hydride to reduce an aldehyde or a ketone. We said it works very well. Well, you can also use lithium aluminum hydride to reduce a carboxylic acid to a primary alcohol. So notice, again, starting with a carboxylic acid, and we end up with a primary alcohol. Now, this is a 2-step process. The first step is to treat it with lithium aluminum hydride. Then the second step is to treat it with hydronium. This is a mechanism that you need, or sorry, this is a reaction that you need to memorize, okay? The reduction of a carboxylic acid with lithium aluminum hydride to an alcohol. However, there are other ways that you can do this. And what's cool about this reaction that I'm going to show you right now, this one right here, is that it's what we call chemoselective. And I think this is the first time this word has shown up in organic chemistry with you guys. It's that we can use borane THF instead of lithium aluminum hydride to reduce a carboxylic acid, again, to that primary alcohol. And the reason why this is such a neat reaction is, again, it's chemoselective. Chemoselective, what that means is that it will reduce the carboxyl group. However, it can reduce it in the presence of an ester or a ketone or aldehyde or ketone or aldehyde. Okay, so maybe I could write the word ketone a little neater there, or ketone or aldehyde. So you see here that we have a ketone, and then we have our carboxylic acid over here. Well, we reduce that to a primary alcohol, but the ketone remains completely intact. Okay, it doesn't get touched. So that's what we call chemoselective. It will reduce one functional group, the carboxylic acid group, but it won't reduce a ketone or an aldehyde. And what's cool about this, you might not be thinking about this right now, but there's no need for a protecting group, right? You don't need any kind of group to protect the ketone. And we looked at ways of masking ketone functionality as an acetal, but there's none of that required here. So again, we've got a couple of ways to reduce an alcohol. We can do it with lithium aluminum hydride followed by aqueous acid, or we can take the carboxyl group and we can just treat it with borane, THF, and that will do the same thing. That will give us a primary alcohol. So it says here, identify the reagents that you would use to achieve each of the following transformations. We're starting with bromobenzene, and we want to convert it into this compound that you would call benzyl alcohol. So benzyl alcohol. Well, let's take a look here. I'm going to switch over to a blank document here just to make sure I have enough space. So again, this is question 20.11, and this is A. So we're starting with bromobenzene. That's this compound. And we want to make this compound. This is called benzyl alcohol. So this is CH2. There we go. So this is benzyl alcohol. Whenever you have a phenyl, so whenever you have an aromatic ring and you've got a CH2 attached directly to it, like that, we call that a benzyl, ZYL, benzyl. So this is called benzyl alcohol. All right, how do we do that? Well, you see that we're incorporating a new carbon into the carbon skeleton. And we've already seen in the past couple problems, we saw a way to go from here to benzoic acid by using Grignard chemistry. And we just saw two ways that we could reduce benzoic acid to benzyl alcohol. We could either use lithium aluminum hydride followed by aqueous acid, or we could use borane THF. Either one works. So what's the first part of our chemistry? The first part is going to involve treatment with magnesium in diethyl ether to make the Grignard. Then we treat it with carbon dioxide to make the carboxylate, and then we treat it with acid to make the carboxylic acid. So this is a total of 5 steps, or if you use borane THF, it could be shortened to 4 steps. Let's take a look at 2011B. So this is part B. We're starting with toluene this time. So just plain old toluene. And we want to convert that to benzyl alcohol. Well, now it's a little bit different, isn't it? Because we're not adding a new carbon to the carbon skeleton. We have 7 carbons over here, and we're ending up with 7 carbons. But we do know that we can oxidize toluene because it has benzylic protons, right? All we have to do is treat it with sodium dichromate, sulfuric acid. Oops. Got acid on the brain here. There we go. And we could make benzoic acid just like that. Okay, well, now that we have benzoic acid, again, we could use either one of our conditions, lithium aluminum hydride followed by aqueous acid, or we could just use borane THF to save our tired hands, okay? And there we have it. So what did we do? A benzylic oxidation to make benzoic acid, followed by borane THF. All right. I had a note here for myself in my notes that I'm just looking at, a note in my notes. And I said, well, there's another way that you could make this that's only 2 steps. If you start with toluene, we talked about benzylic bromination, didn't we? If you were to treat this with N-bromosuccinimide, and if you were to heat that up, you would end up with this compound, which is called benzyl bromide. So we have our benzyl, and then we have bromide. Well, then I could just treat this with sodium hydroxide, right? This is a primary alkyl halide. If I treat it with a strong nucleophile, strong base, there's no way I can do an elimination. So all I have to do is treat that with sodium hydroxide. I'm going to get the SN2, and that would also give me benzyl alcohol. Either way, there's nothing wrong with either way. They're both perfectly fine, but this is a good example of how in organic chemistry too, we see all kinds of examples where there's more than one way to affect a transformation. So let's get back into it here, somewhere around here. And let's get more into, or talk a little bit more about all these carboxylic acid derivatives. Right, that's the title of the chapter. Chapter 20 is called Carboxylic Acids and their derivatives. So you can imagine we're going to spend a lot of time talking about carboxylic acid derivatives. Well, it says here that no, the reduction of a carboxylic acid that we did, right? We just learned how to do this. We did it with borane, THF, or we did it with lithium aluminum hydride followed by aqueous acid, right? We notice that that is a change in oxidation state, right? If you think about the oxidation state of the carbon here, and I'm going to allow you to figure that out. This is based off of what we learned in the alcohols chapter. You have 3 bonds to oxygen, 1 bond to an R group, so that's 4 minus 1, so that means your oxidation state here is +3. Your oxidation state is 4, subtract 5, so this one here is -1. So you're going from +3 to -1. That means you're gaining electrons, right? Gaining electrons is reduced. GER, or what do you guys call it in the States? Rig, right? Oil rig. Reduction is gaining electrons. So this is clearly a reduction, but there's lots of reactions that we're going to look at in this chapter where the carboxylic acids will not change oxidation state. For example, whenever you do a reaction with a carboxylic acid and you exchange the hydroxyl for a heteroatom. So for example, if Z is an oxygen or a nitrogen, for example, or a chlorine, okay, then there's no change in oxidation state. It goes from +3 to +3. So here it would be +3. And if it was oxygen, nitrogen, or chlorine, it would still be +3. So no change in oxidation state. So we can't call these, oxidations or reductions. Well, what do we call them? Well, we're going to have to call them something else, but we'll get to that in a second. Now, what are the most common carboxylic acid derivatives that we are concerned about as organic chemistry 2 students? They're all shown in this slide, the ones that we're concerned about the most. An acid halide, which again we sometimes call an acyl halide, but here we call it an acid halide, an acid anhydride, an ester, an amide. And you notice, well, all of these carbons highlighted in green, what do all 4 of these have in common? They all have 3 bonds to an atom that is not carbon. 2 bonds to oxygen, and a bond to an oxygen, nitrogen, or chlorine. Well, if you take a look at a nitrile, it shares some similarities with the rest of these 4 compounds, in that the carbon has 3 bonds to a nitrogen, just like one of the bonds in an amide. And so a nitrile is also considered a carboxylic acid derivative. And if you convert a carboxylic acid to a nitrile, again, there is no change in oxidation state. Here it's +3, +3, +3, and you can double check me on this, +3, and the same thing here, the oxidation number is +3. All right, there we go. So we're going to go through all of these different derivatives, but in case you're wondering, where would I find some of these derivatives in nature? Well, some are more common than others. Acid halides and anhydrides are pretty unstable. They're very reactive, so they make great fodder for talk when we get into reactions, an acid chloride or an acid anhydride, because they're so reactive, there's lots of cool reactions they can do, but they're not really common in naturally occurring compounds. However, esters and amides are mega abundant in nature. For example, if you like the smell of any kind of fruity odor, like it says here, pineapples, bananas, pears, cherries, strawberries, whatever, then you like the smell of an ester because fruity smells come from esters. And you can see some examples here. Another place that you would find esters would be things like triglycerides. So a TGC, a triglyceride, or a wax. So like waxes, like carnauba wax or beeswax or earwax, those are esters as well. And, if any of you have studied biochemistry a little bit or biology at a higher level, you might have spent some time talking about proteins, right? And proteins or enzymes are filled with amide bonds. It's nothing but amide bond after amide bond after amide bond. Anyhow, well, before we can get into the chemistry, if you will, and the reactions of carboxylic acid derivatives, we need to spend some serious time talking about the nomenclature of carboxylic acid derivatives. And you're going to have to kind of strap your skates on for this one and kind of follow me. And it's going to require some serious practice in order to get all of these concepts to crystallize in your mind. Okay, so let's start with acid halides. If you want to name an acid halide, you replace ic acid with ill halide. So where's my highlighter? We replace ic acid with ill halide. If we have acetic acid, we call it acetyl bromide. If you replace this with a bromide. Let me show you another example. Let's say we have, because this is a common name, right? Acetic acid is a common name. What if you had ethanoic acid, right? If you have ethanoic acid, which would be this is ethanoic acid. We do the same thing. Let's say we had this, okay? We would call that ethanoyl chloride, right? We replace the ic acid with ill chloride. So it becomes, watch carefully, I'll try to use the highlighter here, ethanoyl chloride, okay? So there you go. So that's with a systematic name, not a common name. Benzoic acid, again, we just replaced the ic acid with ill chloride and it becomes benzoyl is how you pronounce that, benzoyl chloride. What about the ones that have the alkane and then carboxylic acid, right? So if you have cyclohexane carboxylic acid, again, you replace the carboxylic acid, but you replace it with carbonyl halide. So carbonyl chloride, carbonyl bromide, etc. So if we have cyclohexane carboxylic acid, we change it to cyclohexane carbonyl chloride since we have an acid chloride there. Okay, so there's kind of two rules covered on here. The ic acid to ill halide, and then for the carboxylic acid as a suffix, we change it to carbonyl, chloride, bromide, etc. What about anhydrides? How do we name anhydrides? Well, all you do is replace the name acid at the end of your carboxylic acid, and you change it to anhydride. So where does acetic anhydride come from? Well, hopefully you can see it comes from two molecules of acetic acid that came together and lost water. So since you have kind of an acetic acid portion in this red box, you call it acetic anhydride. Right? Likewise, if you have ethanoic acid, so if you call this ethanoic acid, and I'm repeating myself from the last slide, ethanoic acid, then you would call this ethanoic anhydride. However, nobody in their right mind would ever call it ethanoic anhydride, okay? You would just call it acetic anhydride because it's common. You can also take dicarboxylic acids and make these cyclic anhydrides. So succinic acid, you can make succinic anhydride. Malonic acid, you can make malonic anhydride, so on and so forth. If you have an asymmetrical anhydride, you list the names of the acids alphabetically, followed by anhydride. So since on this side we have a benzoic acid derivative, and on this side we have an acetic acid derivative, you would call it acetic benzoic anhydride. Right, nothing much to it there. Let's see. What else? What about naming esters? How do we name an ester? And trust me, we're going to do some practice on this in a few minutes. Just give me a few more minutes here. Esters are named by naming the alkyl group attached to the oxygen, followed by the carboxylic acid's name with the suffix -ate. So again, acetic acid. So you start by naming the alkyl group attached to the oxygen. And what it means is this oxygen, let me show you. So if you have your ester that looks like this, okay, they're talking about this oxygen. So that means you start with this as your alkyl group. So here you have an ethyl group, so this becomes ethyl acetate, right? You replace ic acid with ate, so ethyl acetate. Here you have malonic acid, right? 3 carbons. So this is diethyl because you have 2 ethyls. Malonate, right? You replace ic acid, so ic acid with ate. All right. The same rules apply. If the ester is connected to a ring, this is cyclohexane carboxylic acid. We've seen that 3 times today. So this would be methyl cyclohexane carboxylate. Right? Again, we replace ic acid with ate. The last one I think that we need to look at in section 20.6 is, there's 2. There's amides and nitriles. If you want to name an amide, you replace ic acid or oic acid with amide. So if we have acetic acid, it becomes acetamide, or sometimes it's pronounced acetamide, but either way. Benzoic acid, we replace the oic acid with amide, so this becomes benzamide. If it's attached to a ring, so instead of cyclohexane carboxylic acid, if we have an amide here, we call it cyclohexane carboxamide. So you replace carboxylic acid with carboxamide. And then the last functional group, I think, no, we're not there yet. There's other types of amides. Okay, so let me just show you something quickly here. If you have an amide that has a nitrogen with 2 hydrogens attached to it like this is called a primary amide. If you have an R group and a hydrogen, it's called a secondary amide. And if you have 2 R groups, then it's called a tertiary amide. So you have primary, secondary, and tertiary amide. So what does it say here? I'm just reading off the slide. It says, if the nitrogen atom on the amide group bears alkyl substituents, their names are placed at the beginning of the name with N, a capital N, italicized, and I know you can't do that with your pen, but if you type it, you italicize it, as their locant. So since we have 1 methyl group here, this becomes N-methyl acetamide. If you have 2 methyl groups, then it would be N-dimethyl acetamide. Other examples would be if you have 2 alkyl groups, so you put them in alphabetical order. I'll show you an example. Let's say you had this. I got acetic acid on the brain. If you had a methyl group and an ethyl group, you would call this N-ethyl, N-methyl acetamide. Right? Again, just using alphabetical order. So E comes before M. We're just following A to Z. All right. And then the last functional group is a nitrile. So if you have your suffix, which would be ic acid or oic acid, you replace it with onitrile. It's kind of long. So acetic acid becomes acetonitrile. Benzoic acid becomes benzonitrile. So there you go. Just replace oic acid or ic acid with onitrile. Well, that was a lot to digest. I know it is because I've taught this class many times. The students are like, are you kidding me? By the time we look at all that. So what I'd like to do right now is take a short break, and I would like you to all give a try to these parts of question 20.12, and then try 20.13 as well. You might even want to start with 20.13 if you're a little bit overwhelmed. I think it's a little simpler to go from a name to a structure. But we're going to start with this when we come back.